All right, good afternoon. Just picking up where we have left off, okay, and we just looked at some of the basics with the FOIL method as well as working with factoring and just kind of picking up in section R4. I had given just a list of problems to go ahead and be looking into. And for what we have in the case of number 77, okay, from section R4, okay, and we have a four-term expression, and now this one happens to be, it's kind of like the way the problem is set up. In a way, I guess you can say that it's kind of like just like like you might have um, like like in a game of darts or whatever. Somebody might throw a dart and give the impression that he or she has hit the bullseye when actually it's like where the dart landed. Rings happen to be drawn around it where it just happens to be positioned or made to look as if it is positioned in the center. And for what we have in the case of this problem, okay, now we have these terms arranged where the alignment is such that the proportions between the second and first, as well as the last and the third coefficients, are such that we can perform factoring by grouping. Okay, and again, this is where we're looking at grouping together the first two terms, and in this particular case, we have 8ax and 18a. Okay, so you have this first pair at the front. And we have at the center, okay, we have the operation that occurs between the first two and the last two terms to be addition, okay, and grouping together the last two terms, which we have to be 20x plus 45. Okay, so I've grouped the pairings, okay, and so we have for 8ax and 18a, again, if I pull out, okay, the greatest common factor, and we have numerically the coefficients 8 and 18, okay, greatest common factor of 8 and 18 will be 2, and common to both terms is going to be the letter A. So the greatest common factor between 8ax and 18a will be 2a. And factoring out 2a from the first pair, okay, we're going to have 4x plus 9. And we can just bring down the plus, and just looking at solely at 20x and 45. Okay, now since we have a constant only with 45, we're not going to have the greatest common factor in this pairing to consist of a variable. And so this is limited to only the highest number that is completely divisible into both 20 and 45, and that number is going to be 5. And we have 5 into 20x plus 45. Okay, so that is going to be 4x plus 9. And looking at what we have, looking at the factorization of each of the groups here, okay, and we have common is the binomial expression 4x plus 9. And for the other factor, okay, that is going to be combining the outside terms in operation, which in this case will be 2a plus 5. And you can always go back and check, like 4x times 2a will be 8ax. 4x times 5, okay, well that would be 20x. And 9 times 2a is 18a. And 9 times 5, okay, that is going to be 45. Okay, so this will be the set of factors we have for this particular four-term expression. Now, looking at what we have in the case of factoring, and we have as we move from 77 to 87, and this item and some of these items, especially the way the book exercises are set up, sometimes the factorization can be probably as much, if not more work for the eyes than actually just focusing on the math itself. Okay, and we have for 87, okay, we have multi-variable expressions in the letters Y and Z. Okay, and so we have for this one, we have 7 y cubed z, and we have minus 40. That's going to be y to the second, z to the second. And we have minus 12y z cubed. And looking at what we have in this trio. Okay, now if you're thinking of going ahead and factoring into binomial expressions, I understand, because we are looking at a trinomial. But first things first, okay, if you're looking at factoring, you might want to make the process as simple as possible. In the case of factoring out any common factors that might be like monomial expressions or something that is simpler than your binomial with potentially raised coefficients. And if you notice with these three terms, okay, we have y common to these three terms, and also have in common the letter z. So we have common in y, we have y of first degree, and in z, okay, we have at least z of first order. So for this expression, okay, now we have the greatest common factor is going to be yz, and looking at taking what we have and factoring. Okay, so you have the 7y cubed z and the rest. Okay, so looking at factoring, okay, so for what we have for yz into the first term, okay, so we've got 7. Y into y cubed leaves us with y squared. And we have z to itself will cancel. Then we have minus 40. And yz into y squared z squared. Okay, this will leave us with yz. And yz into negative 12 yz cubed. Okay, we have y into itself is 1, z into z cubed is z squared. Okay. So at this stage we have at least partial factorization utilizing the greatest common factor. Now, for what we have in the case of the trinomial, okay, this can be factored. And if we look at moving over to the side, and so we have with 7y squared minus 40yz minus 12z squared. If I look at factoring, and again, if you've done enough problems of this type where you can sort of see the factorization in advance, that is fine. Okay, but now for these, okay, we have the degrees of y and z aligned, as well as the coefficients where we can do the factoring by grouping. And again, just taking what we have with this trinomial, again, we have again multiplying the first and the last coefficients. First coefficient we have at 7, last coefficient we have at negative 12. And 7 times negative 12 is going to be minus 84. Right. And just like the other day, so you multiply the first and last coefficients, and for the product that you attain, you want to find the combination that will add up to the middle coefficient, and we have the middle coefficient at minus 40. So if we look at factors, of negative 84, okay, that will add up to negative 40. Okay, all right. Again, you have like 7 times negative 12 is negative 84, but those numbers add up to negative 5. Okay, and if we go with the combination that adds up to negative 40, well, that combo is going to be where we have only 2 and negative 42. 2 times negative 42 is negative 84, and 2 plus negative 42 is negative 40. So looking at what we have with this trinomial, again, with the factoring by grouping, we're going to split up the middle term. And we're going to have a couple of YZ terms with a coefficient 2 as well as negative 42. And if we look at splitting, and my recommendation would be that if you have a positive and a negative term and they're going to be situated in the middle, I would recommend have the negative term at the front and to be followed by the positive. And the reason for that is so that the middle operation, that will separate the groups, will be addition. And you will not have to worry about factoring out negative 1. And we'll have a case like this to arise shortly. But for what we have, okay, so you have 7y squared, and I'll put the negative 42yz at the front. Okay, and looking at establishing, okay, what we have in the case of grouping, okay, and we have in this alignment. Okay, so you have 7y squared minus 42yz, and we have, again, in the middle, okay, got plus, and we have the quantity, okay, we have 2yz minus 12z squared, okay, and looks like I changed the colors for all these. There we go. All right. So looking at splitting up, okay. Okay, so we have with the first group, okay, so we have 7y squared minus 42yz, and the greatest common factor, okay, so we got the terms have y in common, and for the coefficients, okay, we got 7. Okay, so the greatest common factor here is going to be 7y, and into 7y squared minus 42yz. Okay, this is going to be y, and 7y into negative 42yz. Okay, that would be a negative 6z. And bringing down the addition. Okay, and looking at the next pair. Okay, so you have 2yz minus 12z squared. And for the greatest common factor, okay, now we have even coefficients, and have z also common, and we'll end up with 2z as the greatest common factor, and dividing into this binomial. Okay, so we're going to have y minus, and 2 into 12 is 6, z into z squared is z. Okay. And again, we have from this factoring by grouping, okay, we have the common binomial with y minus 6z And combining the outside terms in operation, okay, we have 7y plus 2z. And looking at what we have in terms of the overall solution. Okay, so going back to the initial setup. Okay, so we started out with in 87. Okay, we had the greatest common factor at yz, which we had factored out, and this trinomial. Okay, again, we had to be factored out, and again the factors left over. Okay, we have again y minus 6z, and the quantity is 7y plus 2z. And just putting back, and so for the final answer for 87, you got yz times the quantity of y minus 6z times that of 7y plus 2z. All right. Now, looking at what we have for the case, and this will be something that is going to be much quicker to solve. And we have in the set, we have for number 90, and say just like for items in ALEKS, okay, even for simpler trinomial expressions, okay, it is kind of procedure heavy. What I mean by this, especially when it comes to simplifying. Okay, now we got p squared plus 8p plus 16. Okay, and again, this is factorable expression, and just as x squared goes to x and x, p squared goes to p and p. And again, for this trinomial, we have factors of 16 adding up to 8. And so we'll have 4 and 4. And this time around, again, looking at the factorization, we have the same binomial factored out, and it appears twice. And condensing and just writing, indicating that p plus 4 is what's regarded as a repeating factor. Okay, we want to have, since it appears twice, again we have for p squared plus 8p plus 16, this is a squared trinomial, meaning that this is going to be the square of a particular binomial, or in this case we had the binomial to be the quantity of p plus 4. Now, also in the case of what we have with this, where I think we're going to have a set of squared trinomials, if we look, we'll go ahead and look at 94. Kind of put that before 91. In 94, here we have the expression to be in the letters m and n. Okay, and we have for this trinomial, okay, we have 9m to the 4th plus 42m squared into the 4th plus 49 into the 8th. Okay, and we have degrees in m and n present in this expression. However, m and n are not both shared for all expressions. Okay, first term is missing the letter n, whereas well, we have the variable m shared only between the first two terms and the last term missing. And it's going to turn out that for 9, 42, and 49, the highest number divisible into these coefficients is only 1. So we have, so there's no greatest common factor to itemize or lay out, just like YZ from the very start. And so looking at what we have with where we can factor by grouping, okay. Again, so looking at the first and the last coefficients, okay, so you have 9 and 49, and the product of 9 and 49 It'll be 441. Okay, so for what we have in looking for the factors of 441, again we had utilized 9 and 49. However, that sum comes out to 58, but we want the combination to be where the sum is at 42. And it's going to turn out, now 441 has several factors, but there's one distinct, or I should say one combination, okay, that will add up to 42, and that's going to be 21 and itself. So 441 is a perfect square value, and it's going to be the square of 21. And we have with this trinomial, the middle term that we have in m to the second, n to the fourth, that we split up into terms with the coefficient 21. And so looking at splitting up, okay, so now we have in the factoring by grouping setup. Okay, so I have 9m to the fourth. And you have plus 21m squared into the fourth. Plus 21m squared into the fourth. Plus 49 into the eighth. Okay, so got the four terms in the expansion, and looking at grouping. Okay, so pairing up the first two items, and we have the middle operation. Again, we have with addition, and we can group together the last two terms. And looking at drawing out, okay, the greatest common factor for each. Okay, so for the first two terms, okay, we got the highest number divisible into 9 and 21. That is going to be 3. And also we have common to both terms is the variable m, and it's not going to be just m, but the lower degree to which m is on display. In this case, this is going to be m squared. So 3m squared into 9m to the fourth. Okay, so that is going to be 3m squared. And we have 3m squared into 21m squared into the fourth. So this would be 7 times n to the fourth. And again, so bring down the addition. Now for the last two terms, okay, we have n shared in common, and the highest coefficient divisible into both 21 and 49. Okay, that is going to be 7, and the greatest common factor is going to be 7. And again, for the lower degree display for n, that's going to be n to the fourth. So the greatest common factor in the second pair is 7n to the fourth, and into 21m squared into the fourth plus 49n to the eighth. We have 3m squared plus 7 times n to the fourth. And we have 3m squared plus 7n to the fourth in common. And combining the outside terms in operation, turns out that we have another 3m squared plus 7n to the fourth. And so this is going to be another case of a squared trinomial. And so for what we're going to have in the outcome, we're going to have the square of the quantity of 3m squared plus 7 into the fourth. Okay, and with the factoring by grouping, again, that is one approach, and we've had the middle operation, okay, to be addition, but now there is going to be a bit of exception to the rule in terms of being able to use addition in the middle, and I'll get to that in just a moment. Okay, and we have with see we have in 91. It's kind of going back. Okay, so for 91, okay, now this expression, okay, we're going to have at least x in common, okay, and y is limited to being present in both the second and the last terms. And for what we have with the coefficients, okay, we have even numbers with 50, 160, and 128. However, in spite of having large numbers that are even, it turns out that the greatest common factor is going to be limited to only 2x. And looking at drawing out, okay, the greatest common factor. Okay, so 2x into 50x cubed. Okay, so you're going to have 25. X to x cubed is going to be x squared. For the middle term, okay, we have 2 into 160 is 80. X into x squared y. Okay, this will leave us 1 degree in x and y left over. And then 2x into 128 xy squared. We have 64. X goes completely into x. And we have the y squared to remain. All right, so we have looking at setting things up for the complete factorization. All right, so we got 2x as the greatest common factor for this trio. And after 2x, I still have, again, a remaining trinomial that can be factored. And so, again, looking at what we have with 25x squared plus 80xy plus 64y squared and it's going to work down. Okay, so if I look at multiplying the first and the last coefficients, so you got 25 at the front, 64 to follow, and 25 times 64, okay, we'll have a 4-digit product. And now involving the number 80, again, you're looking at the numbers divisible into 1600, and that will add up to 80. All right. Again, you'll have to write these numbers, but just kind of show the transition case. So we multiply 25 and 64, however, those values add to 89, so we're just a little bit high. And it's going to turn out that for the combinations of numbers that will multiply into 1600 and that will add up to 80, it turns out that 1600 is a perfect square, just like 441. And that combination adds up exactly to 80. All right. So looking at what we have for this trinomial. So I can set up the factoring by grouping process. Again, so splitting up the middle term. So you got 25x squared plus 40xy plus 40xy, and we have plus 64y squared. And looking at pairing, okay, so first two terms. Okay, so you have 25x squared plus 40xy, and followed by plus, and we have the quantity. Okay, so you got 40xy plus 64y squared, and we have in the case of factoring by grouping. Okay, so we have with 25x squared and 40xy. Okay, so both of these have the variable x, and the highest number divisible is going to be 5. So the greatest common factor is going to be at 5x. And 5x into this duo, okay, we have 5x plus 8y. And for 40xy plus 64y squared, okay, the greatest common factor, okay, we have y in this case, so this is going to be 8y. And this will go 5x plus 8y times. Again, common, we have 5x plus 8y, and the outside terms, when you combine, okay, we'll have 5x plus 8y, and since 5x and 8y repeat, we have this particular factor becomes the square of 5x plus 8y. Okay, so just going back to what we have in the overall picture. Okay, so again we have with 91, 2x was the greatest common factor, and that was the easy part, okay, just extracting the greatest common factor, and then the large amount of the work comes from factoring this trinomial, okay, and this comes out to the square of 5x plus 8y. So we got for the final results in this one. Turns out we have 2x times the square of the quantity of 5x plus 8y. Okay, and just a special case here with the factoring by grouping. we'll say that if you have an expression such as, and we'll say we have, let's say we have 12x squared minus 19x plus 4. Okay, now for this one, the reason I'm throwing this in is this time we have a negative middle term, and looking at trying to factor this one. Again, if you look at the factoring by grouping approach, again, so if I multiply the first and the last coefficient, it's about 12 times 4 is 48. Now I'm looking at factors of 48 that will add up to negative 19. Okay, so we had 48 to arise upon multiplying 12 and 4. However, 12 and 4 come out to positive 16, and we're looking for the combination that will add up to negative 19. And if I change the sign of negative 12 and negative 4, of course that's going to be negative 16, but I want negative 19 as the sum. So in modifying the combination, negative 16 and negative 3, when you multiply, okay, you have the product at 48, and adding together, negative 16 and negative 3 come out to negative 19. Okay, so this is the combination that we're seeking if we're taking the factoring by grouping approach. Okay, so we have upon splitting up negative 19x. Okay, so about 12x squared, and it doesn't matter what order you place the terms. It could be minus 3x minus 16x, or minus 16x minus 3x. And the new situation in this one is that once you group together, you got the middle operation to be subtraction. So once we group together, we got 12x squared minus 16x. Now we have the middle operation is going to be subtraction. And in terms of how to quantify, okay, what's going to be the representation of negative 3x plus 4, think of this as factoring out negative 1 from the pair. So negative 3x will be the opposite sign of 3x, and 4 is the opposite sign of negative 4. Okay, and you can always go back and check. Think of like removing parentheses. 12x squared minus 16x. Remove the parentheses here, and we have minus 3x, and negative 4 comes out to positive 4. All right, so we got the pairings. Okay, and looking at with the factoring by grouping, if we take the greatest common factor of each, so for 12x squared minus 16x, okay, we have an x term and the greatest common factor with 4 divisible into 12 and 16. Greatest common factor will have 4x. And we have into 12x squared minus 16x. Okay, that is going to be 3x minus 4 Now just bring down the minus. And just looking at the greatest common factor of 3x minus 4, well, that's just going to be 1. So just looking at the greatest common factor and 1 to 3x minus 4, that's just going to stick at 3x minus 4. And so for what we have common, okay, we have 3x minus 4. And we have times the quantity of 4x minus 1. And you can always go back and check the results, at least taking the FOIL method. Okay, so we got 3x minus 4. And 4x minus 1, and if you were to FOIL out 3x times 4x, this would be 12x squared. 3x times negative 1, okay, it's going to lead to an outside product of negative 3x. Inside product, negative 4 times 4x is a negative 16x. So we've got minus 3x minus 16x will yield negative 19x. And negative 4 times negative 1 is a positive 4. So I just wanted to throw this in, especially when you have the operation of subtraction in the middle. And I typically try to avoid the subtraction in the middle as wherever I can, but there are some cases where with the factoring by grouping, it's not always, the avoidance is not always possible. Now, in the crossover to other types of factoring, and we have with, I was going to look briefly into this portion, and this is just going to be with the sums and differences of cubes. And for what we have in the case of the sums and differences of cubes, we have like a to the third plus b to the third. Now the formula for this, okay, we have a plus b. And we have times the quantity of a squared minus ab plus b squared. Now for what we have in line with the sum of cubes, I'm going to say that just as an example. Okay, say we have an expression. We'll say that we have, let's say we have x cubed plus, we'll say we have 64 y cubed. Okay, so we got x cubed plus 64 y cubed. And for what we have here, now we got perfect cubes with x to the third and 64 y cubed. But now, to put this in context, so what represents a and b? Okay, now x to the third is already the perfect cube of x. Okay, now for 64y cubed, okay, now you're representing a is going to be x, since x times x times x is x to the third. Now for b, you're looking at the term where that term times itself will give you 64 y to the third. And now for this one, the number of times itself, that will give you 64. It's going to be the cubic root of 64. So that would be 4. And for the the cubic root of y to the third, that is going to be y. So think of like 4y times itself gives you 64 y to the third. Okay. So in a sense, you can say that the a is in reference to x, and b is in reference to 4y. So for a plus b, we'll have x plus 4y and say like a is equal to x, b is equal to 4y. So just taking a bit of an auxiliary approach. So for a plus b, have x plus 4y. Now for a squared, we got x squared and minus a times b so the product of x and 4y. And for b squared, we got b at 4y, which is going to be squared. And for what we have in the case of the follow through, in case you have x plus 4y, and for the resulting trinomial, so we got x squared and got minus now x times 4y. And if I arrange the variables in alphabetical order, so we're going to have negative 4xy. Now for the square of 4y, we got like 4y times 4y. 4 times 4 is 16. And y times y comes out to y squared. Okay, so that will be the result in this case. And now from the group of problems in reference to the sum of cubes. And for number 102, we got u to the third plus 343. And for u to the third plus 343, so we have the sum of perfect cubes. And u to the third, okay, that's going to be the cube of u. 343, that's going to be 7 times itself times itself. So we have on a parallel, okay, so you have a represented by u and b is represented by 7. So for a plus b, we can say we had the quantity of u plus 7. A to the second, we're going to have the square of u. And for minus ab, we have the product of u and 7. And for b squared, okay, so that's going to be the square of 7. And so we have in the follow through. So you have the quantity of u plus 7. We've got u squared. And then we have minus u times 7. So we have the subtraction of 7u. And 7 squared comes out to 49. So these are a couple of cases of what we have with the sum of cubes. Now for the difference of cubes, and there will be a part sort of looking at the deriving of sums and differences of cubes whenever we get into topics such as synthetic division. And for a cubed minus b cubed, okay, so the factorization of this one, we have a minus b. We have times the quantity of a squared plus ab plus b squared. Let's say if you're looking at factoring, and we'll say that we have let's say we have 27x cubed minus 8y cubed. And in terms of what's going to represent a and b, will be like the cubic roots of 27x cubed as well as 8y cubed. So for that times itself, that will give you 27x cubed. Okay, that is going to be 3x. And for 8y cubed, that's going to be the perfect cube of 2y. So you can think of a as being represented by 3x and b by 2y. And just going with the literal substitution for a minus b, we have 3x minus 2y. And for a squared, you can see here a is at 3x. We have plus ab, so we have 3x times 2y. And for b squared, okay, so we have 2y quantity squared okay. And so for what we have in the follow through, okay, so you got the square of 3x, so this will be 9x squared, and 3x times 2y, okay, so we have 6xy. And for the square of 2y, or 2y times itself, okay, that is going to be 4y squared. And we have from the set where the existence of a difference of cubes occurs, we have in 106 okay, we're looking at factoring 27m to the 12th minus 64 n to the 9th. Alright, so for 27m to the 12th, okay, again the cubic root of 27 is 3. Now for the cubic root of m to the 12th, you're looking at 1/3 the degree of 12, and that's going to be 4. So you got 3m to the 4th. And for the cubic root of 64 n to the 9th, from 64 I have 4, 1/3 the degree of n to the 9th. Okay, that is going to be n to the 3rd. So we have a at 3m to the 4th, b at 4n cubed, and setting things up. So for a minus b, you know, 3m to the 4th minus 4n cubed. And again, if you can see the squares and all that in advance, that's fine. Okay, but you got a at 3m to the 4th. So with the a squared portion, we say 3m to the 4th squared. And for the plus ab, so we have the product of 3m to the 4th and 4n cubed. We have plus b squared okay. So the a minus b part, okay, that is already locked in. So 3m to the 4th minus 4n cubed. And we have with the completion of the trinomial. Okay, so for the square of 3m to the 4th, 3 squared is 9. Square of m to the 4th will be m to the 4 times 2. So that'll be to the 8th. So you have 9m to the 8th. Then we have plus, we got 3 times 4 is 12. M to the 4th. N to the 3rd. And for the square of 4n cubed, Okay, 4 squared is 16. And for the square of n cubed, we're looking at n to the 3 times 2. So that's going to be n to the 6th. And this will be the factorization of what we have with this particular difference of cubes. All right. And okay, so far we have dealt with direct algebraic expressions, and we're going to be looking into is where we're going to be looking at rational expressions and operations. Okay, so for what we have in the case of rational expressions and operations, and now in section R4, okay, there's an item, and it's sort of placed in advance, okay, because we normally, I would think that, or in many textbooks, very likely they go into the topic like the domain of a rational function, and for what is referred to as restricted value. Okay, for a restricted value, okay, restricted value is going to be a value is going to be a value outside the domain of a rational function. We can say value outside the domain of a function. And in the capacity of working with fractions or rational expressions. Yeah. So if we're looking at determining the restricted value or values, and we'll say we have in case number 1, okay, let's say that if we have if you have x plus 1 over x minus 4. Okay, now for rational expression, for fractions, okay, the restriction is going to be that the bottom part of a fraction, namely the denominator, cannot be 0 in value. Okay, so you can divide into 0, but you cannot divide by 0. Okay, so for the restriction, okay, x minus 4 cannot be equal to 0. And if that is the case, if x minus 4 cannot be 0, no, x cannot be equal to 4. So the restricted value in this case is going to be 4. Okay. Another case here. Say if you're looking at simplify, and you're looking at determine the restricted value or values. And we'll say that if we have an expression we'll say we have x cubed minus 16x, and we'll say we have all over x cubed plus 6x squared plus 8x. Okay, now if I'm looking at simplifying the ratio, okay, so we have was x cubed minus 16x over x cubed plus 6x squared plus 8x. If I were to simplify, notice we have in the numerator, okay, so you have x we have times the quantity of x squared minus 16, and then we have in the trinomial at the bottom, okay, we have x in common. And looking at the complete factorization of the numerator and denominator. Okay, so for x cubed minus 16x, the complete factorization, you have x times the quantity of x squared minus 16, which goes to x plus 4 and x minus 4. And for what we have in the denominator, so you have x, if I factor x squared plus 6x plus 8, we have x plus 2 and x plus 4. And looking at simplifying, okay, I held out on the cancellation of x until I got to the end. Okay, so we got the complete factorizations. Now, if you notice between the numerator and denominator, okay, we have a common factor with x. And in simplifying, okay, those will cancel out. And also between the numerator and denominator, we have x plus 4 in common, so those will cancel. And for what we have in the case of simplifying, okay, so you have x minus 4 all over x plus 2. Okay, so x minus 4 over x plus 2. Now, in terms of the restriction, the restriction is going to be in reference to the original form of the ratio. So again, the denominator, the original denominator, not the simplified, not in the simplified ratio, but in the original. Okay, so you have x cubed plus 6x squared plus 8x cannot be zeroed. And just looking at the factors again, so you got x and x plus 2 and x plus 4, okay, cannot be 0. So if the whole expression cannot be 0, okay, we have none of these factors can be 0 either. So from x cannot be 0. From x plus 2, x plus 2 cannot be 0. Okay, so we have that x cannot be negative 2. And from x plus 4, if x plus 4 cannot be 0, we have that x cannot be negative 4. So in this case, the restricted values will be this trio, and it does not matter what order they come in. Okay, so you have 3 restricted values. Okay, so you have 0, negative 2, and negative 4. And the reason we have 3 is that in the original ratio, if you plugged in any of these into x, you would have a 0 valued denominator. Okay, now where we have operations between functions, or what could be referred to as combining like ratios, if you're looking at adding and subtracting. And let's say that if we have if we're looking at combining into a single expression. Okay, and just kind of get things started here. Okay, so if I have like terms, and we'll say that we have, say if we're looking at combining into a single expression. Okay, I'll give you just like a cupcake example. Okay, say if you have rational expressions that already have the same denominator. Say I have 3 over 7 plus 5 over 7. We got the same denominator. And so you can combine the numerators. And so 3 sevenths plus 5 sevenths. You say it was 3 plus 5 over 7. So this will come out to 8 sevenths. All right. And let's say that if I change things up a little bit, okay, and we'll say that we have okay, if you notice before we had the same denominator with just 7, but now by adding x and y of different degrees, okay, so we have, for the first ratio, I have 3 over 7x squared y to the 5th, and I have plus 5 over 7x to the 4th y to the 3rd. Okay, and for what we have in this case, all right, to be able to combine, okay, I need a common denominator. And if I put in terms, the ratios in terms of the least common denominator. Okay, now, again, least common denominator will be the smallest term that both of these denominators will go into. Okay, so, and we already have 7 for the numerical coefficient. Now for what we have in x and y, we have x squared and x to the 4th. And so this time we have the higher degree in x to be in the least common denominator, so that would be x to the 4th. And for what we have with y, we have y to the fifth, y to the third. So the higher degree, and y we have y to the fifth. So the least common denominator is going to be 7x to the fourth, y to the fifth. And just looking at what we have in adjusting the ratio. So we got 3 all over 7x squared y to the fifth. And if I put this in terms of the least common denominator, okay, so we already have 7x squared into x to the fourth. So we have x squared left over. Y to the fifth is already present in the first denominator. Okay, so I'm going to multiply the first ratio by 1 in the form of the number of times that the first denominator goes into the least common denominator divided by itself. So this will be x squared over itself. And for what we have in the second ratio, okay, so for 5 over 7x to the fourth, y to the third. Okay, so we already had the 7 and the x to the fourth. So now we've got y to the third relative to y to the fifth. Okay, so if I take y cubed into y to the fifth, I'm going to need y squared. And if we work across, okay, so if you notice in both of the products in the denominator, okay, so I have 7 x squared times x squared is x to the fourth. We got y to the fifth. And guess what? 7x to the fourth, y cubed times y squared is also 7x to the fourth, y to the fifth. And I can go ahead and combine the numerator terms. So I have 3x squared plus 5y squared, okay, and that will be the single expression result for this one. All right. And tell you what, looking at what we have with ratios, just a couple of items here. Okay, so if we're looking at simplifying and determining the restricted value or values. Okay, well, let's see what we get in the case of x squared minus 9 all over x squared plus 5x plus 6. And for what we have in the case of combining as a single term, or combine into a single term. I will say that in this one, let's say if we have So I tell you what, just for the next few moments, let's see what we get for the simplified version of this ratio, while also identifying the restricted values. And also, let's see what we get with the sum of these two ratios. Okay, so looking at what we have with the first item, and again, so we have x squared minus 9 all over x squared plus 5x plus 6. And if we look at simplifying this ratio, all right, so you have with x squared minus 9, then we have the difference of squares. Okay, so this will factor to x plus 3 and x minus 3. And for x squared plus 5x plus 6, so the binomial factors, we will have an x plus 2 and x plus 3. So we have x plus 3 in common. And just for the simplified form, okay, we have the reduction to x minus 3 all over x plus 2. All right. So this is a simplified form, but it's not like the exact same terms. We're just looking at a proportion. Okay. Now for the restricted values. Okay. Now the restriction is going to be, again, that the denominator cannot be 0. So looking at what we have here, again, and factoring once again, so we have x plus 2 and x plus 3 are the factors of the trinomial, and x squared plus 5x plus 6 cannot be 0. Okay, but we have that the factors cannot be either. Okay, so if we have at the one end x plus 2 cannot be 0, we have that x cannot be equal to negative 2. As for x plus 3, if this cannot be 0, we have that x cannot be negative 3. And so we have with the restricted values, there's going to be with negative 2 as well as negative 3. Now, in the case of operations, okay, between ratios, okay, that have unlike denominators. Okay, so here we have 3 over 2x squared y to the 4th z cubed, and we have plus 1 over 4x to the 5th y to the 4th z. And looking at what we have in the mix, okay, so we don't have the same denominator, and if we put in terms of the least common denominator, okay, so with the numbers 2 and 4, smallest number that both 2 and 4 will go into, okay, that would be 4. And for x, okay, we'll be looking at the higher degree representation of x. In this case, this is going to be x to the 5th. And for y, okay, we have y to the 4th present in the denominator of both terms. And for z itself, the higher order, we have it z cubed. So least common denominator, we have 4x to the 5th, y to the 4th, z cubed. And taking what we have with the ratios and expressing in terms of the least common denominator. So for 2x squared y to the 4th z cubed into the least common denominator, okay, so we got 2 into 4 is 2. And we have x squared into x to the 5th, so we have x cubed. And we already have y to the 4th, and we have z cubed present as well in the denominator of the first ratio. And for 1 over 4x to the 5th, y to the 4th z, okay, we already have 4, and we also have x to the 5th, and we also have y to the 4th. Okay, but now for z into z cubed, okay, this is going to be z squared. And looking at consolidating, okay, so both denominators, about 2 times 2 is 4, x to the 5th, y to the 4th, z cubed. Likewise over here, 4x to the 5th, y to the 4th, z times z squared is z cubed. And looking at the numerator expressions, okay, so we got 3 times 2x cubed. So that'll be 6x cubed, and then we have with the other numerator, we have 6x cubed plus z squared. And this will be all over 4x to the 5th, y to the 4th, z cubed. All right. Now, there are other operations in the mix in terms of working with rational expressions, and I'll give you, at least in the case of adding and subtracting, there are a couple of items I do want to address. I've done this with some of my other classes, and this is where you're looking a little bit into prime factors. At least in the first example, and I just want to mention, okay, so if you're looking at combining into a single term, I do want to mention, okay, and let's say that if you have 3 over 8x squared y cubed, and we'll say we have plus 1 over 10 we say x to the 5th y, and we'll say we have minus, and we'll say that we have in this particular mix say minus 2 over 25 y to the 4th. Okay, and we have for this one, okay, if I'm looking at the least common denominator, okay, some of you might be able to get to the least common denominator quickly, and that's fine. I just want to mention something about, like, if you're looking at, say, prime factorization. What I mean by this is like prime numbers. Those are those natural numbers that factor out to 1 and the number itself. And now for 8 is what's referred to as a composite number. And if I do prime factorization, if you think of two numbers that will go into 8, you might think of 2 times 4. Now 2 is a prime number, for it factors to 2 and 1. Whereas in case of 4, it is not a prime number. In addition to factoring out to 1 and 4, you have 2 and 2 as well. So I'm going to expand on out. Now for the prime factorization of 8, we have 2 times 2 times 2, or 2 to the third power. Now for the coefficient 10, this will go to 2 times 5. Both 2 and 5 are prime numbers, and guess what? For 25, this factors out to 5 times 5. Okay, and so we got prime factors. With the numbers 2 and 5. And for the variables involved, okay, so we have x and y. All right. Now, if we're looking for the least common denominator, okay, what's going to happen here, okay, is that if you look at 2 and 5, you're going to be looking at in the case of 2, you'll be looking at the greatest number of appearances from any one of these 3 factorizations. Notice we have with 25, there's not a 2 that appears. 10, it appears once. And from 8, it appears 3 times. So the least common denominator, again, is going to involve 3 2's. And for what we have in the case of 5, it does not appear at all from 8. It appears once from 10, and it appears twice from 5. And for the variables x and y, okay, you're looking at the highest degree representation out of the denominators. So we have for x, highest degree representation is going to be to the 5th. And for what we have in y, that's going to be y to the 4th. So for the least common denominator, we got 2 times 2 times 2 is 8, times 5 is 40, times 5. So this will be 200. X to the 5th, y to the 4th. And looking at taking what we have with the ratios. Okay, so we'll raise in terms of the least common denominator. Okay, so just working with what we have. There we go. All right, so we got for the first ratio, so you got 3 over 8x squared y to the 3rd. So we'll raise this. Okay, so putting in terms of the least common denominator. Okay, 8 into 200, we got 25. X squared into x to the 5th. Okay, so that is going to be x to the 3rd. Y cubed into y to the 4th. Okay, so that is going to be y. And we have in the case of the second ratio, okay, so you have 1 over 10x to the 5th y. And putting this ratio in terms of the least common denominator. Okay, so you have 10 will go into 200 20 times. And we already have x to the 5th. And for y into y to the 4th, okay, that's going to be y to the 3rd. And for the last ratio case, we have for for 2 over 25 y to the 4th. Okay, so 25 into 200, this will be 8, and we need x to the 5th. And we already have y to the 4th in the last ratio. All right, so taking what we have, again, all the ratios will have the denominator to be 200x to the 5th, y to the 4th. And now looking at what we have among the numerators. So you got 3 times 25. Okay, so you have 75 x cubed y. And the next term we have 20y cubed. And for the last, okay, we'll have minus 16 x to the 5th. And that'll be the final result in this case. Now, we're going to be looking at rational expressions even further. But I tell you what, I'm going to go ahead and cross over to what we have in working with equations. And now, for equations we'll be dealing with, okay, there are some categories and types. Okay, some might have limited numbers of solutions, some might have an infinite number of solutions, and you also might have those equations that will lead to no solution at all. Okay. And in crossing over, okay, among our categories, and just to kind of give the lay the groundwork. Okay, we have types of equations. Okay, one type we have conditional, another type we have as a contradiction. We have as remaining category, okay, we have an identity. Okay, and for what we have in terms of what defines the categories. Okay, now for a conditional, a conditional is going to be an equation with a limited number of solutions. Okay, now like if you have an equation that has like one right answer, that's a conditional. Or if you have 2 solutions in the equation, that is also a conditional. You're looking at a finite number of solutions. And we'll just take like as a case of a conditional. If you're looking at solving for x, and you have 2x plus 5 is equal to 17. You can see we have with this equation, again, we're solving for x, and if we kind of go through the conventional approach of isolating the variable term, which we have a 2x, again, we can take the subtraction property of equality, and so here we have 2x equals 17 minus 5, which is 12. And then we have with division, so undoing multiplication by 2. or dividing by 2. Okay, we'll end up with x equal to 6. Okay, so this equation is true as long as, or on the condition that x is equal to 6. 2 times 6 is 12. 12 plus 5 is 17. All right. Now, in the case of a contradiction, okay, that's going to be an equation with no logical solution. And just in case here, if I have, let's say, trying to solve for x, and I have 2 times the quantity of x plus 3 minus 4, let's say we have is equal to x plus 5. Okay, so for what we have on the left-hand side of the equation, okay, so if I distribute 2 over x plus 3, so we have 2x plus 6, and we have the subtraction of 4 to follow, and to the right we have x plus x makes 2x, and we've got plus 5, and combining the constants on the left, so I have 2x plus 2 is equal to 2x plus 5. And here we have like terms on opposite sides. Okay, so we have in the letter x, have 2x and 2x, and with the constants, I have 2 on the left, 5 on the right. And let's say that if I combine like terms, say if I gather what I have in x, well, guess what? If I combine the x terms, I'm looking at subtracting 2x on both sides, and what results here is that everything we have in x is going to cancel out, and what is going to be left standing will be numbers that will be said to equal each other when in fact they do not. Okay, so here we have x goes out. I mean, the math was done correctly, and so we're trying to say that 2 numbers are said to equal each other when in fact they are not. And so what happens here is that we could try to plug in a negative value, 0, or select a positive value for x, and there's no real number in x where both sides in this equation will equal. Okay, so in this case there is no solution, and trying to say that 2 numbers are equal to each other when they are not, okay, that's like an application of a contradiction. And we have in the category of what we have with an identity. Okay, and an identity. Okay, you will have an identity is going to be, you will have an equation that's going to land an infinite number of solutions. This is sort of a limited definition, but it does kind of serve the purpose. and it's going to be an infinite number of solutions in the sense that the logical premises, okay, will be consistent. And let's say that if you're looking at a case of an identity, say if you're looking at trying to solve for x, and let's say we have 3 times the quantity of x plus 4 is equal to x plus 6 plus 2 times, okay, the quantity of x plus 3. Okay, so for what we have on the left, okay, so if I distribute, so we have 3x plus 12 to the right. I have x plus 6 at the front, and distributing 2 over the quantity of x plus 3. Okay, so we have 2x plus 6 so left hand side, okay, we have a 3x plus 12. Right hand side, okay, so we have x and 2x, so this will make 3x, and 6 plus 6 is 12. And this time, okay, so we have kind of a setup with like terms at opposite sides. And if I gather the 3x's, subtracting both sides, kind of like what happened with 2x, we got a cancellation. But this time around, the numbers that remain, okay, we have 12 on the left, 12 on the right, and this is a true statement. And so what that means is that, okay, so if you have x to go out and you have numbers left standing and they are said to be equal to each other and the statement is true, what this signals is that you can plug in anything for x regardless of whether you have a negative value, a 0, or a positive, and you will have both sides to equal each other. So in this case you will have an infinite number of solutions, and there are ways you could express what we have for x. One way could be symbolically, like the capital R. Let's say we have all real numbers. And there's another notation. This is going to be in the case of interval notation for all real numbers. This would be parentheses surrounding negative and positive infinity. Again, this is a case of an identity. Okay, so you have a logical consistency throughout, and where we had landed 2 numbers said to be equal to each other, and in fact they are. And so that again is the green light where we could plug in anything for x in the real number system and both sides agree. Alright, and for what we have in the case of equations, okay, you have equations of varying degrees, and one that we're going to be looking at quite a bit, especially throughout the course. So we have with quadratic equations, and those that involve second degree expressions, and we've looked at factoring like terms in x squared and squares of other variables. But now in the case of where you have like a second order trinomial or difference of squares, involved in an equation okay, and we have by definition, and we have for a quadratic equation a quadratic equation is going to be a second degree equation whose standard form you have a quadratic equation, you have a second degree equation whose standard form is going to be ax squared plus bx plus c is equal to 0, whereupon a is non-zero in value. Okay. And again, just for a second degree equation, just stressing this second degree, we're looking at the highest order in the variable that we're solving for. So in this case, you have ax squared. And again, the premise is that a is non-zero in value, and if it were, you would no longer have an x squared term, and you would have at most a linear equation. Okay. And now there are various routes that can be taken in terms of solving quadratic equations, and an introductory one is in the case of what is referred to as the zero product property. And for what we have in the case of the zero product property, and this is not limited to just two terms, but the general case often presented in textbooks does have it as like two terms a and b, where if you have that, if the product of a and b is 0, so if a times b is equal to 0, and if that is true, then at least one of those terms must be 0. So it might be that a is equal to 0, or it could be that b is equal to 0. I say that in the case of quadratic equations, okay, say if you're looking at solving for x, okay, and we'll go with a standard layout already. Okay, so say we have let's say we have x squared plus 7x plus 10 is equal to 0. So we got x squared plus 7x plus 10 is equal to 0. And this is where I had the feel of like what we looked at when we looked at restricted values, but where we had the trinomial or expression could not be 0. But here with quadratic equations, okay, we're looking at where it is equal to 0. So for x squared plus 7x plus 10, okay, so x squared factors out to x and x, and again for the constants that will multiply out to 10 and add up to 7. So we have 2 and 5 or 5 and 2. Okay, so we have in this scenario, okay, we can set the factors equal to each other. And if x plus 5 is equal to 0, okay, so we have that x is equal to -5. And if, on the other hand, x plus 2 is equal to 0, we have that x is equal to -2. And for this equation, you can go back and check for -5. If I square -5, like -5 times -5, that is 25. 7 times -5 is -35. 25 and -35 will be -10 plus 10 is equal to 0. Same thing for -2. -2 squared is +4. 7 times -2 is -14. 4 and -14 will be -10. -10 plus 10 balances out also to 0. And this is a case of, for this equation, okay, this is like a conditional that results in two solutions. Right? This equation is true on the condition that x is -5 or +2. Okay. Now let's say that if I change things up a little bit, and let's say that if we have an equation still quadratic, but the display is going to be somewhat different in the introduction. And let's say if I have x squared plus 36 is equal to 12x. I'm looking at solving for x. Okay, first of all, it's the standard form of a quadratic equation is where you have the variable terms on one side and 0 on the other. And so in this one, I have x squared plus 36 is equal to 12x. Now this, in a sense, is a quadratic equation, but it is not laid out in standard form. And I can adjust this. So I got x squared on the left, and I can make the value on the other side, or expression on the other side, to be at 0. So I'm just going to move the 12x over. Upon subtracting, and just combining the terms and arranging the expression in descending degree order. So I have x squared minus 12x plus 36 is equal to 0. And if I look at factoring, for x squared, okay, so this will go to x and x. And factors of 36, that will add up to -12. Okay, so you have x minus 6 and itself. So we don't have distinct factors, we just have a repeating linear factor. So you got a repeating factor with x minus 6. So that means that there's going to be only one solution. So I just need to put down x minus 6 equal to 0 once. And from this, there's one solution for this equation, and that is going to be the number 6. Now let's say that if you have a little bit of a different case and still working with a quadratic, and let's say that if you have a coefficient in front of the x squared. Let's say if you have -2x squared plus 8x plus 64 is equal to 0. Okay. And I can think of at least a couple of pathways you can go about solving and still utilize, okay, the zero product property. Okay, now this equation is in standard form. Okay, and if you notice, okay, we have even valued coefficients throughout. And let's say that if you want to use the 0 product property, you can make the negative 2x squared into x squared. And in fact, what you can do is that with negative 2x squared, you can divide the whole equation by negative 2. If I do this, okay, so if I divide the equation by negative 2, it's not going to have any impact on x. So negative 2x squared divided by negative 2. This will be x squared. And we have 8x divided by negative 2. That will be a negative 4x. 64 divided by negative 2. That will be a negative 32. Okay. And so this becomes a more conventional display. Okay, so just lowering the absolute value of the coefficient. So dividing by negative 2. So I have x squared minus 4x minus 32 is equal to 0. And it's from this stage that I'm at liberty to use the zero product property in this capacity. So we have with x squared minus 4x minus 32. From x squared, okay, we're going to have x and x. Factors negative 32, whose sum or difference will be minus 4. More weight will be given to the subtraction than to the addition. So here I'm going to have plus 4 and minus 8. And looking at what we have here. Okay, so setting x plus 4 to 0. I'm going to have the x is equal to negative 4. And for x minus 8 equal to 0, I'm going to have the x is equal to 8. And so in this case, we have two solutions for x. One at negative 4 and the other one at 8. And tell you what, just in the case of looking at solving equations, and we'll say here, if we're looking at solving for x, let's see what we get in the case of let's say we have x squared so we have x squared plus 20 is equal to 9x. And we'll say we have 3x squared plus 30x plus 75 is equal to 0. So for the next few moments, okay, let's see what we get for x with these two equations. I'm going to show you a couple of ways how to go about the second case here, but just looking at the equations now, the first equation we do not have set up in standard form, whereas in the second case we do. And for the first item, okay, so you have x squared plus 20 is equal to 9x. And if I rewrite this equation in standard form, okay, that is, have the x squared first order x and the constant, non-negligible constant on one side and have 0 on the other. So I can make this type of transition upon moving the 9x over. So subtracting 9x from both sides. Okay, so we're going to have x squared minus 9x plus 20 is equal to 0. And here, okay, so we got the standard form translation of this quadratic equation, and I can set things up where I can factor and follow through with the zero product property. Okay, so we have an x squared, so this will go to x and x, and then factors of 20 that will add up to -9. Again, two ways that a pair of numbers will multiply into a positive, and so we have both to be either positive or both as negatives. Okay, so in this case, adding up to -9, we have -4 and -5. Okay, so you have from these binomials of subtraction. Okay, so if we set the factor x minus 4 equal to 0, then we have x equal to 4. And for x minus 5 equal to 0, we have that x is equal to 5. Okay, and say, like if I test out 4, 9 times 4 is 36. Let's swap 4 squared is 16. 16 plus 20 is also 36. And with x at 5, 9 times 5 is 45. And 5 squared is 25. 25 plus 20 is also 45. So 4 and 5 do check out consistently. Okay, now for what we have in the case of the second equation, okay, now we're going to have a common factor since the coefficients 3, 30, and 75 are multiples of 3. So I can do here is I can just divide the equation by 3. And if I do so if I divide the equation by 3, okay, so 3x squared divided by 3 is x squared. 30x divided by 3 is going to end up at 10x. And 75 divided by 3, so that's going to be at 25. So you have in the rewrite, so you got x squared plus 10x plus 25 is equal to 0. And we have with this trinomial, after the division, turns out we're going to have yet another situation where we have the same binomial factors. So again, we have that x plus 5 is a repeating factor. Since we have a repeat, let me just one use of x plus 5. And if I set this equal to 0, so if I have x plus 5 equal to 0, we're going to come out to x is equal to -5. Okay, and another route, okay, say that if you did not divide by 3, let me just show you another pathway here. And I'm actually debating on whether to do this, but I'm kind of thinking that maybe not for the introductory chapter, but for subsequent sections down the road, Alex might give it like a factored form of this, and one might be wondering if if there are more x factors to work with than there actually are. I'll just show you this route. Say if you have, again, 3x squared plus 30x plus 75 is equal to 0. Okay, and just like from the start when we looked at like our expressions that had like the y's, the z's, the m's, the n's, where 3x squared plus 30x plus 75, if you were to factor, what you do is that you can factor out 3, and 3 will go into 3x squared, x squared times 3 into 30x is 10x, and 3 into 75 is going to be 25. And for x squared plus 10x plus 25, 3 times x plus 5 times x plus 5 is equal to 0. And if I were to just put this in factored consolidated form, this is like 3 times the square of x plus 5 is equal to 0. And let me mention, okay, so with this 3, is just a constant, not an x factor. So it's not doing anything with x, like adding, subtracting, multiplying, dividing, or even doing anything exponentially. And with the square of x plus 5, again, you have the same kind of situation here, but through a different pathway. X plus 5 is a repeating factor, so just the only solution in x will come from just one use of x plus 5. X plus 5 is equal to 0. Again, distinct pathways, both still correct and both still arriving at the same result, okay, whereupon we have that x is equal to -5.